there is an explicit equation associated with each one of these things, and that's it. I mean, if I wrote the whole thing out, it would fit on the second line here. Okay. And that's it. That's a complete definition of all the scattering amplitudes. You can put it, it's a 3-line code in Mathematica. You press return, and you can have on your laptop the 17-particle for-loop amplitude. So it's a complete definition of the theory where the words space-time, Lagrangian, path integral, gauge symmetry, and so on make no appearance, as promised. And it works. So 2 years ago, people using the most cutting-edge technology of the time had done calculations for scattering in this theory. I'm giving you an example of scattering amplitude with so-called 2 loops. And they had written the answer. And this is, again, vastly, vastly better than finding diagrams, which we've just written down the answer. And it looked like this. Various kind of topologies, and they had various sort of coefficients like this, and there were 8 more pages that looked like that. Okay, so that was 2 years ago. This is the current situation. The entire previous 8 pages is the top line. I haven't told you what those wiggly lines are. Trust me, they're not just defined to be the previous 8 pages. Okay? So, but these are objects which are not natural to a person thinking about space-time loop integrals. They're ultra-natural to people thinking about Riemannians and twistors and projective geometry and all of these polytopes and everything that I was telling you. So when this one-term expression matches the previous 8 pages, and you can check them on the computer, they match perfectly, then you know that A, it's working. Then B, you calculate things that had never been calculated before. So no one had calculated the next most complicated 2 loop amplitudes. Well, here they all are, they fit on a line. How do we know they're correct? Well, you know, if you go to enough particles and lengths, I mean, they're 2 very simple terms, but there's lots of permutations of these things that you have to sum over. So, you know, let's say you go up to 25 external particles. There's 10,000 terms there. Each term isn't local and isn't unitary. Then you check, is the whole answer local and unitary? Yes, it is. Let's say you flipped one of the signs. No, it isn't. Let's say you deleted one of the terms. No, it isn't. Okay? You have to take every single thing that's there with the signs as they come out, and only then does it work. So then that starts convincing you that it's probably right. None of the 3-loop amplitudes had ever been computed. Here's all of them. They all fit on a line. And it's just a question of boredom. I mean, one of my grad students just decided last week to write down all the 4-loop amplitudes, and it'll probably be done by the time we get home. Okay. So it works. Now, that's the story for the integrand. I told you we still have to integrate them to get the final answer. So could it be that the simplicity is just there at the level of the integrand, but then things get horribly complicated when you finally get the answer? And doing things the conventional way, you certainly think things are going to get complicated. For example, for the simplest case of 6 particles and 2 loops, if you actually did the calculation, first you get those 8 pages of finding diagrams. That's the first thing. Then you'd actually try to compute them using Feynman's methods. Okay? I don't mean well, it's not all Feynman's fault, but still, he gave us these, using the Feynman parameterization, Feynman integrals, Feynman everything. You do it the best possible way, and what you get is this answer. You don't even need to know what these objects are, but just to know that they're complicated polylogarithms, and there's 17 pages that look like that. And yet, by using very, very similar mathematical structures that go into the first discussion that we're talking about, in the last year, people realized that this result could be simplified to a line. So even the final answer, after all the integrals, has some astonishing simplicity to it. So I hope you're convinced that there is something very wrong with the usual way of doing things. There's something new that's starting to emerge. I won't tell you some of these things, but I also, that what you've seen in this last 10 minutes is that we're seeing pretty strange pictures. Planes and n dimensions, these weird wiggly line things, polytopes. These are very, very combinatorial ideas, very far from the usual sorts of mathematical structures that we're used to dealing with in physics. And it's just amazing that they're sitting here at the heart of thinking about scattering amplitudes in a new way. And I should also say that this whole superstructure of mathematical concepts that go in here fit into an umbrella to a part, to a sort of deep part of math and algebraic geometry in particular that was developed by the infamous French mathematician Grothendieck in the 1960s. This is kind of a wing of math which is not the wing of math that had been interacting with physics so closely in the last 30 years. And what's remarkable is that the physics knows more than both the mathematicians and the physicists do. It knows that even this very abstract combinatorial part of mathematics seems to have some role to play. Okay, so let me just end by recapping. The 20th century gave us two revolutions, space-time and quantum mechanics. In a sense, the intellectual pinnacle of how far we can go with both of these ideas as they were handed to us, basically unmodified, is to realize that they're different aspects of the same thing through this correspondence between theories of gravity and Gates theories in one lower dimension. But we have further to go. And I think certainly what we have to come to grips with is emergent space-time and perhaps even deformations of quantum mechanics. Although here, not in silly situations, but only in cosmology. This all seems like a very tall order, but as I said in the beginning motivations, one way to attack them is to figure out how to talk about the physics we have under our feet in a way where locality and unitarity are emergent notions. And so we have to understand how even in standard situations we can understand, we can see the emergence of locality and unitarity from more primitive notions. And I think we're starting to see that. We're not there yet for the full story. It's only at the moment for this maximally supersymmetric theories, only in the simple limit, this planar limit. There's a long way to go to completing it to a full picture. But it's finally some very concrete evidence that this program might actually go somewhere. Because we see that from these totally different starting points, K-planes, polytopes, twisters, and so on, we're getting a direct picture with actual quantum local processes, which is so simple and direct precisely because it doesn't put into space-time and the unitarity as such. It doesn't give them such a starring role. Okay. And this is allowing us to see physics more invariantly without all these gauge redundancies that we always have. Gauge symmetries, general covariance, these are all complete fake. These things don't exist. Okay. But they're complete fakes that were incredibly useful in our development of physics in the 20th century. But we have to start learning more and more how to do without them. And this is a way of seeing, at least we're starting to see how that can happen. This has already been a very long colloquium, but I should say that there are many other threads of research, totally unrelated to the subject, apparently totally unrelated to the subject, involving other aspects of quantum field theories, which amazingly show up exactly the same mathematical structures, literally exactly the same mathematical structures make an appearance in totally different kinds of physical questions. So it really feels to many of us that we're in the midst of an extraordinary period of our understanding of what field theory can actually do, with possibly deep consequences. There's no guarantees, but possibly deep consequences for a picture of what space-time and quantum mechanics are. But as it should also be clear from the fact that this colloquium has gone over time, if we really understood it, we could explain it without going through this long, circuitous song and dance, first this, then that, then the other. Just give the answer. So the grand synthesis hasn't happened yet. There are sort of storm clouds, but it hasn't broken. When it does all make sense, then I think there's a good chance it might come to some fruition sometime in this decade. Maybe earlier, maybe later. But that's the sort of timescale that I suspect will be involved, at least for the next for the next stage of this story. Then you should invite someone else or whoever does it to come and give the colloquium in less than an hour, and it'll be all very nice. Okay, thanks a lot. Thank you.
Long but very entertaining colloquium, so we'll just take a few questions, and I'm sure you already put will come down and talk.
Yes, certainly.
So a couple of questions.
It seems to me that you actually gave us two talks, not because of the time I took, but it breaks up into two parts, naturally. The first part where you made these very provocative and interesting statements, which you said were not speculative, and I said they were. And then the second talk was this one on this rather brilliant mathematical physics, which is not at all speculative, it's calculational, and it makes calculations meaningful
Yes.
instead of being 80 pages long. There didn't seem to be a very close connection between these two. For example, this one you said it was not manifestly local, but in the end, you do all the calculations, it calculates out, cancels out, so that, yeah, it really is local after all, and that's a good check. That doesn't support the notion of space-time not being fundamental but being emergent. It was there all the time. You just found a clever calculational way that didn't depend on it.
Well, I mean, so I make the analogy again with the principle of least action. The principle of least action isn't different than classical physics. It is classical physics. But it's a way of talking about classical physics that is the closest possible jumping off point to get to quantum mechanics. Because when you think about classical physics in that way, you've pulled the 95% of the trick. You figured out how to talk about actually exactly deterministic physics, secretly exactly deterministic physics, in a way that's not deterministic. And that formulation is the one that's closer to being deformed to the correct theory. So that's the idea here. The idea is first reformulate. Of course, that's the whole point. We have a check. We check that it's local, and we check that it's unitary. But it doesn't look like a sequence of tricks. It looks like there's a whole structure sitting there. And this structure does not care about locality, and it doesn't care about unitarity, just like the principle of least action doesn't care about determinism. So there's a second step which hasn't happened yet because we haven't completed the first step. We haven't really completed the one-sentence statement, it is the principle of least action. Okay? We haven't completed that part, but if it's completed, the idea is that it would suggest a natural deformation that would be the analog along from the principle of least action to a quantum mechanics by the path integral. Here it would deform it to something else that would tell us how to sensibly deform these notions of locality and unitarity as appropriate. But actually, a little more specifically, because I didn't have a chance to describe it, an even longer talk would have made the connection more clearer. But there